All right, it's time to get started. Welcome back. I'm glad to be here. Hope you are too. We are going to start talking about our last major consequence of completeness. That's what we've been doing the last couple times. We had the nested intervals property is a consequence of completeness, and also the last time we talked about the density theorem for Q inside of R, that every in between any two real numbers is a rational number. Today we're going to talk about another consequence of completeness, which concerns the cardinality of R. Cardinality. This is a word that you may have seen in discrete math. I'm not sure, but this is something that I want to talk about. The cardinality of R. Cardinality is a fancy word to mean, when you see this word, you should think of it as like size, as in how many things there are in a set. That's what the cardinality is. So the cardinality means it's the number of elements in a set. And so, for example, the cardinality of the set 5, 6, 7 is, what do you say? 3 is the answer, yes. Because there's 3 things in that set, all right? Now, I'm not usually going to write this like card of whatever, but you know what I mean by that. The cardinality of a set is the number of elements in the set. Now, this number can be finite, like a number, or the cardinality is not always a number, because the cardinality, sometimes you can have a set which is infinite, right? Has infinitely many elements. So, sets like, for example, N, Q, R, these all have infinite cardinality, as we all know, because they are not finite sets, right? These all have infinite cardinality. What I want to talk about today, and this is a big theorem. This actually, I think, I've been thinking about this all day. I think I'm going to go out and say it. I think this is my favorite theorem in all of mathematics. Can you believe it? I can remember learning about this as an undergrad, and kind of blew my mind. And I hope that it'll blow your mind, or at least you'll see why someone's mind might be blown by this. N, Q, and R all have infinite cardinality, but not all the same cardinality. It is simply a fact that there are more than one size of infinity. You can tell your friends on the playground this. If they ever ask you about infinity, they're like, oh, you're a math major? You know about infinity? And you're like, yeah, I guess. They can say, is infinity a real thing? You can say, yeah, kind of. And actually, there's more than one size of infinity. There's like little ones and big ones. In fact, there's more than 2 sizes of infinity. These are the things that I want to talk about. Did you discuss this in your discrete math class? I don't know. You probably talked about some of the things that we're going to talk about. Anyway, these 3 cardinalities of N, Q, and R, they're not all the same. Actually, 2 of them are the same as the other, but they're not all 3 the same. I will tell you that, so the infinity measuring the size of N is smaller than the infinity which measures the size of R. In my opinion, this whole line of thinking, the way of reasoning about different sizes of infinity, to me, this is like, I think in a lot of ways, this is one of the great achievements of human intellect in human history. You know, until this was first done, so let me just say this was done in the main ideas here are from like the 1870s. The mid 1870s is when this was done by a German mathematician named Cantor. And before the time of Cantor, mathematicians were deeply uncomfortable about the idea of infinity. People had talked about things like from calculus, when you do stuff like this, or things like this, a sum where the variable goes up to infinity. These are things that people had done for a long time before the 1870s. But limits in calculus, or limit of a sum like an infinite series or something, those were not viewed as the language they use is weird to us from a modern point of view, but they said something like, these kinds of limits are representative of like a process, and you imagine if the process were to continue forever, it would somehow tend towards a certain result, right? Whereas Cantor's point of view is, no, I'm not thinking of infinity as some kind of ever unachievable end destination of an infinite long process. Cantor actually thought of infinity as like a thing which exists fully by itself. Like, I think the word they used was, he thought of the infinity as like, they called it the completed infinity, like an infinity which doesn't require some kind of endless process to achieve. But Cantor's idea was like, you can actually talk about infinity as a thing by itself, something that actually exists, not some kind of mythological process or something. This was a big idea and very, very controversial at the time. Even though it was like pure mathematics, a lot of mathematicians said like, infinity, we just shouldn't talk about it. Or infinity is sort of like in the realm of philosophy or even theology, and it is not appropriate for mathematical discussion. And Cantor was like, yeah, but I proved a theorem about it. So, you know, it is mathematical if you can really prove things about it. And in fact, there were some people who accused Cantor of trying to like kill God or something. Like, infinity is something that is like only God is infinite or something like that. And if you try and prove theorems, and you're like transgressing on some sort of boundary line that mathematicians shouldn't cross. And but Cantor was like a devout Christian, and he said like, well, I believe that my theorem was like spoken to me by God. He actually said that. So what are you going to do with that? Very, very interesting sort of philosophical business behind it. But anyway, it was believed for a long time that the concept of infinity was kind of like off limits to mathematics, and Cantor showed that actually, no, it is not. We can prove theorems about mathematics. And I've even had people tell me things like, yeah, you know, people can never understand God because God is infinite. And, you know, I guess I understand what you're saying, but the sort of, mansplainer in me wants to say like, well, actually, we can understand a lot of things about the infinite because there's different blah, 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 blah. I try to resist the urge most of the time to say things like that. Okay, anyway, Cantor, so Cantor really is regarded as the inventor of, or the founder, I'll say, set theory. In order to do this, nowadays all of mathematics is based on set theory. Everything you learn in an advanced presentation of mathematics is about sets and operations on sets. Everything's about sets. It wasn't like that before the time of Cantor. And one of the reasons is because people didn't really know how to make sense of infinite sets. So they didn't like to think of an infinite set as a set. They thought of it as some kind of process or something, which is, I mean, sure, you can think about it however you want, but that's not a very helpful way of thinking about it if you want to prove theorems. So Cantor, really, in Cantor's work on this, it really legitimized the idea of set theory. And this was the very beginnings of how within 50 years from then, set theory had totally taken over all of mathematics, and everything is done in terms of sets. Anyway, I want to give a little review here. So let's review, first of all, one-to-one and onto. This is about functions from one set to another. I hope these are terms that you've seen before and remember. I will refresh your memory. A function, I want to say for some function with a domain and a codomain. So when I write that, I mean f is a function The domain is X, so the values you plug into F come from the set X. And the codomain is not quite the same as the range, but it means the set where the values come out is some other set Y. We say F is 1 to 1. I'm going to write like this, 1 dash 1. When 1 to 1 basically means if you have two different points in the domain, they go to two different points in the codomain. You never have 2 points in the domain which go to the same point. So the typical way you write this definition mathematically is if f of x1 equal f of x2. So if you do have two different domain points which go to the same answer, you basically want to say that never happens. Then x1 equals x2. So if you think you have two different domain points that go to the same answer, it turns out actually they were not two different points. They had to be the same point. The only way to get the same answer for two values is if they were actually the same value to begin with. All right, this is the definition of 1 to 1. This, in your discrete math class, I hope that you spent quite a bit of time talking about this. And then there's also f is onto. And this one means for any value y in the codomain, there exists x in the domain such that f of x equal y. So this means every value in the codomain is hit by some value of the function. Right? That means it's onto. 1 to 1 and onto. These were not ideas invented by Cantor, but Cantor was the first to look at these two concepts and recognize that they were very important. Of course, these are not deep ideas, really. They're things that anybody would come up with on your own if you were just thinking about functions in general. But Cantor kind of gave some real prominence to these ideas in a way that no one before him had. 1 to 1 and onto. All right. For example, let me just say, if it's both, if f is 1 to 1 and onto, this is special, then f is called, so in our book they say a 1 to 1 correspondence. Correspondence. All right. Means 1 to 1 and onto. Each of these three terms, they have another kind of way of saying them. So 1 to 1 is also sometimes called an injection. Onto is also called a surjection. And then 1 to 1 correspondence is called a bijection. Our book doesn't use these three words, but when I speak to other mathematicians in the club, I usually say injection, surjection, bijection. So I might say those words from time to time. They mean 1 to 1 onto and 1 to 1 and onto. All right. Okay. Let's just to refresh our memory. I hope these are ideas that everybody's familiar with. But here is some little diagrams to give you an idea of how you should think of these. If I have, say, a set of 3 points and another set of 3 points, like let's say this is my x and y, and my function tells you how to get each value of x goes to some value of y, and if my function looks like this, let's say that one goes there, that one goes there, and this one also goes there. Is that big enough? Whoa. Big it up. All right. Is that clear? I'm going to do this again. What? Okay. All right. Just to make this very clear. Like this. All right? Is this 1 to 1? What do you say? I see the heads shaking. No. Yeah, it is not 1 to 1. It's because we have two values in the domain here which go to the same answer over here. That is not allowed for a 1 to 1. So this is not 1 to 1. This is like those two values go to the same place. You might say that's 2 to 1 on those two values at least. Okay, and is it onto? What do you say? Also, no. Why is it not onto? The last dot, yeah, this dot right here has no x going to it, and so that means it's not onto, all right? Any questions about that? I hope everybody is, I'm just trying to refresh your memory about one-to-one and onto. How about this one? How about if we have two dots like this, three dots over here, and you go like that and like that. What do you say? Is it one-to-one? I believe it is one-to-one this time, because you always have a single domain goes to a single value in the codomain. So this one is one-to-one. Is it onto? It is not onto, because the values don't cover up everything in the codomain. So because of this point, which nobody goes to that point, it's not onto. All right? It's possible that, here's an example where it is onto but not one-to-one. How about if I have like this? This one is onto, but it's not one-to-one. You can see it is onto because all the points in the codomain get hit by something. So this is onto, not one-to-one, because these two, the two upper dots get mapped to the same point. That is not one-to-one. All right. What does one-to-one and onto look like? Well, it means every point gets hit, and also no two points get sort of doubled up. So something like on a diagram like this, maybe that. This is one-to-one and onto. All right. This is one-to-one and onto. So you can say it is a one-to-one correspondence. All right. Here's another memory in my past. I remember when I was in college, I went to a math conference once with one of my professors, and it was me and one other student who was kind of a nice-looking young girl, shall we say, and she was getting a fair amount of attention from some guy at the conference. And this is one line. This is a direct quote from this guy. He was trying to impress this girl who I was with. I was with her. She was just another student who went with me, right? He was trying to impress her, which is totally fine with me. I had nothing to do with her. She was just on the trip with me. Anyway, he said, and I quote, "Yeah, I mean, whenever I want to show something's a bijection, I just show it's an injection, and then I show it's a surjection." And at the time, I thought, is this guy like trying to say something impressive somehow, or is he just like saying the definition of bijection? And I asked my professor afterwards. No, he was just saying, I still wonder why he said that. I don't think he impressed her by saying that. Would have been fine if he did, but I don't think he did. Okay, this is one-to-one and onto. I hope we all remember what one-to-one and onto means. I will have you notice, and this is the important sort of realization that Cantor had about all of this. It is only possible to have a bijection, or one-to-one correspondence, if the two sets have the same number of dots in them, right? If they have different amounts of elements, then you cannot make a one-to-one correspondence. So I'm going to say two sets have the same cardinality meaning how many, the number of elements in them. If and only if there is a bijection between them, or I should say one-to-one correspondence. All right, two sets have the same cardinality. The only way that's possible is if they have a bijection. The way that it's typically thought is the only way you can have a one-to-one correspondence between two sets is if they have the same number of elements, right? The same cardinality. But this right here, Cantor took this idea, and actually this is not a theorem according to Cantor. He said this should be a definition of what the word cardinality means. So instead of thinking of cardinality as like the number of things in it, he just said, well, two sets, they have the same cardinality if you can make a bijection from one to the other. And Cantor realized we can do this even for infinite sets. even if two sets are infinite, you can still ask the question, is there a one-to-one correspondence between these two sets? Even if they're infinite, right? You can still try to decide if there is a one-to-one correspondence. So in this case, actually, there's a notation that our book uses. This is not a universal notation, but we're going to write it this way. When there exists a one-to-one correspondence, let's say f from some set A to B, then we're going to write A squiggly B. And this means A and B have the same cardinality. Or A and B, you should think they have the same size. So for example, the set 1, 2, 3 has the same size as the set 5, 6, 7. I mean, obviously it does, but according to the definition, technical definition here, what that means is there is a bijection from the set of the numbers 1, 2, 3 going to the set of the numbers 5, 6, 7, a one-to-one correspondence, all right? That's what it means. And it also means they each have 3 things in them, all right? Like I said, though, this is really most interesting when you're talking about infinite sets. So here is an example using infinite sets. How about n versus, I'm going to call this set E. And E, I'm going to write as the set of even numbers, 2, 4, 6, 8, etc. All right? Welcome back. Do these have the same cardinality or not? Informally, that means are they the same size, or is one bigger than the other? All right? It turns out they do have the same cardinality. Even though E is a subset of n, in that sense, E is smaller than n because all the stuff in E is also in n. But actually, they have the same cardinality. These are the same cardinality. What I'm saying is n is squiggly. I don't know how you pronounce the squiggly. N and E have the same cardinality. That's how I pronounce it. All right? Let's try and justify this fully here. What it requires is you have to create a one-to-one correspondence. So we need, I'm going to write this as if it were a proof. It's not very difficult, but we need a function, f, which goes n to e, right? And then we need to demonstrate that that function is one-to-one and onto. So maybe it would help to write our set this way, 1, 2, 3, 4, etc. And then E is 2, 4, 6, 8, etc. And we want our function to go sort of this way, right? You plug in one of those n's, and you get out an even number. Let's use f of x equal. Anyone want to give me? You can like say with an ordinary formula of a function. How do you get from the top set to the bottom set? 2x, yeah. F of x equal 2x. If you plug any natural number into that, you get an even number as the answer. Can we demonstrate that this is one-to-one and onto? So I'll say I want to show it's one-to-one and onto. So for the one-to-one, remember the definition of one-to-one, which I wrote a few moments ago? It was if f of x1 equal f of x2, then x1 equal x2. So what we do is we assume f of x1 equal f of x2, and then I want to show x1 equal x2, right? That's the definition of one-to-one, says if f of x1 equal x2, then x1 equal x2. Any thoughts about this? How can we proceed if we have assumed f of x1 equal f of x2? Since f of x1 equal f of x2, what can you do with that? Yeah. Yeah, we just like plug into the definition of f. F of x equal 2x. So this means 2x1 equals 2x2. Remember, we need to show x1 equal x2. Can you do that? Yeah, what do you do? Say. Divide both sides by 2. Yeah, it's like an old-fashioned math class now. We divide both sides by 2. So x1 equal x2. Shoon. Right? That's what we wanted to show, that x1 equals x2. Excellent. Okay, so it is 1-to-1. How about onto? Remember what onto means? It means for every value in the codomain, which in this example is e, there is some x value which goes into that value in the codomain. So I'm going to say take any y in e. That's a y right there. And I want to show, or let me say it this way, we'll find some x in n with f of x equal y, right? This is what you need to do to show something is onto. We begin just with y in e. What can you say about just the assumption that y is in e? Well, that means y is even. And typically the way we write, when we know something is even, we write it this way. So I'll say since y is even, we have y equals 2k, right? For some k in the natural numbers. That's what even means. Anybody see then? How can we show, we need to demonstrate that there is some x with f of x equal y. Really, I would like to say, the end of my proof should say something like, so y equals f of something or other. Can we fill in the blank here? We have to show that y is f of something. Yeah.
The f of 2x?
I don't think it's f of 2x. Remember what f is? The definition is f of x equal 2x. I heard something. What did you say? K. Yeah, f of k, isn't it? If you put k there, f means 2 times whatever, right? F of x is 2x, so f of k is 2k, and y is 2k. So y equals f of k, as desired, right? We needed to demonstrate that y equals f of something, right? And it does equal f of k. So both of these things together show that f is a 1-to-1 correspondence. So that means that n has the same size as e. The set of all natural numbers is the same size as the set of just the even numbers. When you tell your friend on the playground this, they will threaten to stop listening to you. You say there's more than one size of infinity. They're like, but then you also tell them that the number of even numbers is the same amount as the number of all numbers. That's if you think of it from a certain point of view, that doesn't make a lot of sense. But it's true. Both of those things have the same infinite cardinality to them. All right. Here's just another very quick example, and then I have one for you guys to try. Yes. Okay, how about this? How about n versus this other set? There's nothing really special about this set, but so n is the set of all the natural numbers, just starting with 1, 2, 3, etc. And then s, I took just some other set of natural numbers where you start at 10,000 instead of starting at 1. But you still just count up from there. All right? Can you make a bijection from one of these sets to the other to demonstrate they have the same cardinality? So actually, they do have the same cardinality, even though S just is the same as N, but it's missing 10,000 of the first elements, but maybe 9999. Anyway, N is the same cardinality as S using the function f, well, maybe I'll just write f of x equal. Anyone think of what's a function you can use to get from the set N into the set S? Yeah.
X plus 10,000.
Yeah, x plus 10,000, or maybe 9, yeah, just technically 9999, right? You're totally wrong, man. No. Yeah, excellent. So this is also a bijection. I don't think we need to go through the proof, but you can prove it very, very easily the same way that I did. So this is a one-to-one correspondence. Actually, in discrete math, probably you talked about the fact that something is a bijection if and only if it has an inverse as a function. And this function does have an inverse. You can add 9999. The inverse would be subtract 9999. All right. I brought up this example in particular because this example actually appears in the classic American church song, Amazing Grace. Anybody know what I'm talking about? So the last verse of Amazing Grace, to my knowledge, the only religious song which includes a true fact about transfinite cardinalities. That's what this is all called. The last verse is about when we all go to heaven, and it says, when we've been there 10,000 years, bright shining as the sun, we've no less days to sing God's praise than when we first begun. So it says the important parts when we've been there 10,000 years, right? It's about when we're in heaven for 10,000 years, we've no less days than when we first begun. Meaning, if somebody goes to heaven and they're there for 10,000 years, the duration of time which remains for them in heaven is the same amount of time as it was when they first arrived in heaven. That is to say, N and S have the same cardinality, right? When you take away 10,000 things from the beginning, it doesn't actually change the size of this infinite amount. All right, way to go. I don't know if, I believe Amazing Grace was written before Cantor did his work. I doubt that there was any influence between the two of them. But interesting fact, I always like that, whenever I hear that verse of the song, paradoxically, it makes me feel smarter than everybody else around me. Because I'm like, yeah, I know about infinite cardinalities. Not a good posture to have when hearing a church song, probably. Okay, let's talk about, all of these have been related to N. How about for real sets? I mean, sets of real numbers. For example, let's consider this. The closed interval from -1 to 1. And the closed interval from -10 to 10. It turns out they have the same cardinality. Can anyone think of a function that can bring you from one to the other? Yeah. 10x, yeah, f of x equals 10 times x. This will take any number between -1 and 1 and transform it into a number between -10 and 10, right? And it is a bijection. This you would have to go through checking a little, but actually, we already showed f of x equal 2x is a bijection. So would you believe me that f of x equal 10x is exactly the same thing, just replace all the 2's by 10's. So this is a bijection, or this is a one-to-one correspondence. And so those two intervals have the same cardinality. How about, I want to do you all to try, can you show that -1 to 1 has the same cardinality as 0 to 1? So your job is write down specifically a function which goes from one to the other, and then see if you can demonstrate that your function is a bijection. Actually, it might be a little easier. I don't know. I'll have you decide. You could do it the other way around if you want. Instead of a function which goes minus 1, 1 to 0, 1, you can make a function which goes 0, 1 to minus 1, 1. Maybe you can think about which you think is a little easier. So come up with a function, f of x equals something, and then see if you can show that your function is 1 to 1 and onto. I'll give you a few moments. I'll come around and see what you think. Feel free to talk to your neighbors. If you're still trying to think of a function, you could think of this. If I wanted to do, for instance, f going from, let's say, 0, 1 to minus 1, 1, you could try and think of this like you would maybe in a calculus class. I want the domain to be 0, 1, and I want the codomain, the range, it will also equal the range, to be minus 1 to 1. So can you invent a function which has that particular domain and that particular range? You could probably just draw a line which has that domain and that specific domain and range. Maybe that would help you come up with the function. You don't have to think of it in that way, but that's one way you could think of it. Good idea? Actually, I think that goes the other way around, but that's it. Maybe it. So you want a function which has this function. So you could make it just like a line which fits in that picture. Where the domain is the thoughts? Idea? Squared. X squared is not 1 to 1. Because, like, minus 1 squared equals 1 squared. It only has to be one. The other way actually would be. Yeah. So now show that it's not.
It's gone. Yeah.
See if you can show this.
Okay.
This, all right. Or you use your function. Yeah, it's not one. So don't use the other.
There's one that works.
Yes.
Oh, I didn't know that.
That does work for them.
Yeah, that file.
It does complicate.
Yeah, this is possible to do. This is not one of those easy to figure out in docs here. So now show that it's not one. It's part of your job. Find the function and then show that it's one-to-one and onto. I'll give you another 4 minutes. Yeah, that's right. Yep. Still thinking? Can you make the equation for that line? It's not. I think it has to. The slope is not one. It's good. Can you show it's one-to-one and onto?
How do you want us to do it? Just plug it in?
Hmm?
How? Just like plug it in?
No, like this. It's with this. This is how you show it's one-to-one. This is how you show it's onto.
I've got your basically, so sure I can.
Yeah.
It's for this.
Oh. If you want to do it this way, then
It's a different, yeah, got it, okay, thanks.
yeah. Anywhere? No. You do x minus 1. So
Yeah.
the diagram that I drew is for domain 0 to 1. Just x minus 1.
Yeah.
You can find the equation.
So there's no use.
Well, that's true.
So that's my-
This line here was all right, let's talk about this. I saw some people with varying amounts of success here. If you follow my suggestion here to find the function, its graph would look something like that, where this is 1 here, this is minus 1, this is 1. That's 0, of course. This is a function whose domain is 0 to 1, and its range is minus 1 to 1. And the equation of that line would be f of x equals 2x minus 1. Another way to think of this, maybe, without looking at this picture, is just think about if I begin with some numbers from 0 to 1, and I first of all multiply them all by 2, then those numbers are going to go from 0 to 2. And then if I subtract 1 from all of those, they will now go from minus 1 to 1, which is what we want here. Or you can think in terms of this line. Anyway, we got to show that this is 1-to-1 and onto. How do we show it's one-to-one? I saw at least one person said we assume f of x1 equals f of x2. This is how you always show something is one-to-one. So that means 2x1 minus 1 equals 2x2 minus 1, right? You plug into the function. And then what can we do with that? We need to conclude x1 equal x2, but we can first add 1 to both sides. So 2x1 equal 2x2, and then divide by 2, so x1 equal x2, which is what we wanted to show it's one-to-one, right? And how about onto? We take any y in the codomain, which is minus 1 to 1. Then we want x with f of x equal y, right? Did anybody do this part? Yeah.
And then x would be from 0 to 1.
Right?
What?
Yes?
Oh, yeah. And then since y equals 2k minus 1 and k is in 0 to 1, so then f of k equals y. So that's it.
I'm not sure that is what I would say. You got to tell me what k is.
That's what it is. That's what
Did you? Yeah.
I said f of k exists in the set of 0 to 1, but then you have to plug k in.
Yeah. So I would. Here's how I would show something is onto. In this case, you know, the example we did a few minutes ago with just 2x was quite a bit easier, I think. For this one, with this weird equation, 2x minus 1. We have y is in minus 1 to 1. We want to find some x which has f of x equal y. So I'll say it like this. I want f of x, instead of writing f of x, I'm going to write 2x minus 1 equals y. We can solve that for x, right? And that will tell us what the x value is, which ends up equaling y when you plug it into the function. You can solve this for x by adding 1. 2x equals y plus 1, x equals, so y plus 1 over 2, all right? And if you believe me, then it's true that f of y plus 1, sorry, yeah, actually that is what I wanted to say. F of y plus 1 over 2 equals y. It's because we chose the x in such a way to make it such that 2x minus 1 equals y. Is this, sorry, I feel like I'm not saying this very well here. Then, this is not wrong what I wrote, but I'm going to, come on now. All right, sorry. Let me say it a different way. So then I'm going to say let x equal y plus 1 over 2. And then we have, what is f of x? It's 2x minus 1. But if x is y plus 1 over 2, then this is 2 times y plus 1 over 2 minus 1. And if you simplify and cancel all that business, you get y, which is what we wanted. Right? What we have to show is that f of x equals y, and that's what we did. The trick, you know, the tricky part is really like, how did you just pull that out of nowhere? X equal y plus 1 over 2. I didn't pull it out of nowhere. I pulled it out of this. This is how you figure out how you came up with that y plus 1 over 2. All right. We got 1 minute. Can I just say one more thing? So, what all of this conclusion was that 0, 1 is the same cardinality as minus 1 to 1. All right? Also, can I just say this way? Similarly, any two closed intervals have the same cardinality. Right? The interval from 0 to 5 is the same as the interval from -10 to 6. How do you see that they're the same size? Well, one, you can just sort of scale it up by multiplying it by something, and then you can shift it around by adding and subtracting certain values. So in the example we just did, it was 2x plus 1 you got to do. That's scale it up by a factor of 2 and then shift it to the left by 1. But whatever the intervals are, you can always figure out how do you need to scale it, how do you need to shift it. All right? Next time we'll talk about actually why some of these infinite sets have different sizes. That's the interesting part. I'll see you then. I hope you have a good weekend.